Okay, welcome everyone, and thank you for joining us today. My name is Laura Clark. I'm VP of Communications for the DDS Foundation, your host for this evening. Before we get started, I'd like you all to know this presentation will be recorded, and the views expressed by the speakers are theirs alone and do not necessarily represent that of their respective organizations. Okay, so for those of you watching this virtually, please take a moment to note the options on the bottom of the screen to chat, raise your hand, and ask questions. During our forum, feel free to ask questions in the chat. Make sure to virtually raise your hand and we'll answer them during our live question and answer session. It's now my pleasure to welcome my speakers and panelists. Please feel free to stand or wave when I introduce you. I know that those of you virtually can't see them, but in the audience, I'll be able to see you. So our moderator, Shar Wales, Systems Engineer and Process Specialist for Jackrabbit Consulting. Lynne Canavan, VP of Marketing for the DDS Foundation, who will be giving a DDS Foundation overview. Nina Tucker, VP of Engineering for Twin Oaks Computing, who will be giving us a quick introduction to DDS. Nina is also Catholic. Adam Mitz, Principal Software Engineer and Partner of Object Computing. Director of Interoperability at the DDS Foundation. Adam will be talking about the DDS family of standards, and he is also a panelist. Our speakers from Metron, Christine Judd, VP of Metron's Unmanned Systems Division, and Matthew Judd, Autonomy Software Architect and Developer of Metron's Unmanned Systems Division. They will present their use case, commercial resilient underwater autonomy solutions utilizing the DDS standard. And two of our other panelists, Eric Hendricks. Yeah. DDS SIG co-chair and senior software architect at Zetascale, and Andy Krasowski, field application engineer at Real-Time Innovation, and Terrence Milligan, marketing and analytics manager at OMG, who will be moderating the online questions. And now I'll turn it over to Lynne, who will tell you more about the DDS Foundation.
Good. All right, thank you. I'm Lynne, as Laura said, I'm Lynne Canavan. I'm the VP of Marketing for the DDS Foundation. Thank you all for joining us, those of you online as well as those in the room today. This is just a quick overview of what we do, and then you're going to hear from end users as well as the people who are actually developing the standard as well. So thanks for joining, and let me just get right into it. What is the DDS Foundation? Hopefully some of you know who we are, but if not, I wanted to give a bit of an overview. I use a lot of words, so I tried to make really important ones on these slides. We are vendor neutral, so we collaborate, the DDS vendors collaborate tightly to come together in the DDS Foundation. We're vendor neutral, and we are a collaborative nonprofit that was formed to grow DDS usage in the field. So we are orienting towards users themselves to make DDS more compelling for our user community, collective user community to generate and collaborate and share ideas and things like that too. We are comprised of users, end users, government institutions, researchers, universities, and the vendors. What do? We promote the adoption, interoperability, and the success of the DDS family of standards to the wider user community. And so you'll hear from Adam in a little bit. He's going to talk about the standards. DDS is not one standard, it's a family of standards, and he's going to share some of that too. But what we try to do is we are the non-technical, although that can be debated, but we're the part of the DDS group that doesn't do the work on the standards themselves, but we actually promote the standards to the wider community. We collaborate very tightly with our brethren in the DDS SIG, and Eric is here with us today, and he's one of our panelists, and he is one of the co-chairs of the SIG as well. We focus on technology, interoperability, applications, the ecosystem, and then marketing and communications. So the things in the DDS standard and with the DDS standard, again, our mission is to help promote this externally so that you can see all the great things that you can do with DDS. And what our goals are specifically, we consider ourselves a body that are here, again, working with end users to help drive future requirements for the DDS standard. We define industry-specific data models and adaptations of DDS. We focus on vendor interoperability, and we also we are a source for industry education and resources. And much of what I'm going to talk about is going to focus on the latter, the education, the resources. These are the officers. Some of them have already been introduced. Nick Stavros is not in the room, but I believe he's online, and he's our VP of Technology. And otherwise, Laura has introduced us all. And again, Terrence offers us the support from the OMG. And we are open to all, so come join us. You know, there's no charge to attend. There's no cost to attend. We are really an open group looking for additional participation. Okay, so what are some of the things that we have done? One is there is a DDS guidebook, and it is out there and it's published and it's on our website. I'll show you the website, but I just wanted to share that it exists, and it has a lot of use cases. It has things on the technology standard itself and so forth. It's if you want to know what DDS is and how do you know, in general about DDS, it's an excellent place to go and get it. Is the DDS guidebook. That is an ongoing, evolving document. Shar in the room has worked on it, and lots of other people as well. So anyways, it is an ongoing, evolving document. It's not a one and done type of a thing. We have a foundation, the DDS Foundation has a library of webinars and use cases spanning from agricultural to smart manufacturing to healthcare. And so please, we encourage you to go online and look at that. Our webinars, much as today is being recorded, a lot of our webinars are recorded. We also document those. And so we encourage you to use it because all of those are specific end users sharing what they're doing with DDS, and they're a valuable resource for the industry at large. And I just wanted to share a couple of those sample use cases, just so you know, I'm going to encourage you to go to our website and download some of these things too, but this is kind of a sneak peek of what you might see. So CGI they're a UK organization, and they presented a use case on GVA, generic vehicle architecture, and some of the things that, so again, this is for NATO, the GVA. This is a standard, and they were talking about some of their pain points and why they came to use DDS. And so for every one of our use cases and case studies, you'll see what the pain point was that led somebody to choose DDS, what they're doing, what their experience was with it too. So again, I'm not going to present these slides. I'm just going to share that these are some of the things that are in these public documents. And then you get little glimpses of why they use it and how they use it. And so there's things like there was why this organization in particular adopted the DDS standard was, there's no single point of failure, it's scalable, the quality of service and so forth. But you get some insights when you hear a user talking specifically about those different endpoints. Here's a sample use case that was presented by Matt Grubis, who is with GE Healthcare. They've adopted DDS to do patient monitoring. And so he did a webinar with us, and he also he wrote it up as a document. So again, these are some of the things that you will see on the website. A nice healthcare case study there. This was our last one. We had the city of Montreal who adopted DDS, and they came in January, and we had a webinar on that. And he presented about his data-centric approach. And his whole thesis was, they had been using MQTT, and it just did not work for them. And so they switched over to DDS, and it was pretty radical. And so he was sharing such gems such as this. The best way not to move forward is to follow fixed ideas. And so he's a real enthusiast and stuff. That was a terrific session. So again, I encourage you to go back and listen to some of these. We also have been experimenting and trying to promote this at the university level. 2 years, time is running by. Vanderbilt, before the pandemic, one of our last sessions before the pandemic, Vanderbilt came, and they've been doing some things with Kubernetes and DDS, and they presented a kind of a case study on what they were doing and some of their research as well. So again, we're trying to look at it from different perspectives, not just the end users, but universities and researchers and what they're all doing together. So with that said, where do you find this information? If you go to DDS-foundation.org, on the OMG website, just look for DDS, and then you go here and you see at the top, you can look at the resources tab, and that's where you'll find a lot of these resources and information about what DDS is, what the foundation does, some of the solutions, and so forth. Again, encourage anyone who wants to come and join us, please do so. You can see us after this session. You can email us, or you can look on the web and we'll get an email and get back to you on that. And so again, here's their email and here is just the website. And I wanted to, again, thank everyone for coming today. I hope you enjoyed this session. And with that, it's my pleasure to introduce Nina Tucker, the VP of Engineering for Twin Oaks, who is going to be talking about DDS, like a quick introduction to DDS. Thank you.
All right, everyone. So again, my name is Nina Tucker. I am with Twin Oaks Computing. We are a DDS vendor. That means we've developed an implementation of these DDS standards, and we license it and support it and do all kinds of fun stuff with it. Anyway, I'm here to give the super short introduction to DDS. Usually these tutorials and introductions go an hour, 90 minutes. We're going to try and do it in 10. Let's see how that goes. So I'm going to start by talking about just some of the common characteristics of connected systems. First of all, they're dynamic, right? Components come and go, things expand, things change, data types change over time. They are distributed. You've got some edge components, perhaps. You've got sensors, actuators. You've got other intermediate sort of components. You might have back-end components in the cloud. Lots of different components to these systems that have to communicate. They are decoupled. In a lot of cases, components need to be able to operate independently or in absence of other components. You need to be able to handle and adjust to networks dropping out or different components coming and going. The common challenge across all of these kind of different systems and all of these industries is how do you build a robust data infrastructure across all of these sorts of challenges and all these sorts of devices. So the Data Distribution Service, DDS, is a high-performance communication middleware standards. We heard about the family of standards. That provides this robust data communication infrastructure. It is a publish subscribe technology. It has additional APIs for client service, RPC type functions. It is inherently decoupled. There are no brokers, no central points, or no single points of failure in the DDS architecture. It is scalable. So you can find the DDS APIs and feature set all the way from very embedded DSPs, PLC sorts of devices, through devices with real-time operating systems, through mobile devices, through desktops and servers, all across the board. And DDS is secure. It includes within the standards and within the protocols, authentication of endpoints, access controls, integrity and confidentiality of data streams. So the data distribution service, you heard Lynne mention this, you'll hear this again from Adam. It really is a family of standards. I like to say that DDS is fully standardized. And what I really mean is that there's standards that cover a lot of different aspects of data communication. So we have a standard that talks about the API, I should say standards, that talk about the API for DDS. We have another standard that talks about the wire protocol. So what that means is you have standardization where you have a common API across programming languages, across operating systems, across different vendor products, providing you portability. And then on the wire protocol side, you have interoperability. So you can connect your devices, again, different languages, different operating systems, different devices, different DDS vendor products, and they will all plug together. And then in addition to that, you have quality of service, or the behavior of your data communication streams is also standardized. So you can define the timing requirements and the reliability requirements of each data stream. And then you have data type representation in the standards, allowing you to very cleanly define the kinds of data and have type safety within your data communications. And then of course, security, the end-to-end security is standardized. So that just gives you an example of all the different aspects that are standardized with this technology. And then of course, it's a vibrant community. I mean, we're here right now during OMG Technical Meeting Week, where this morning we met with the DDS PSIG.
we do continuously evolve these standards and adopt new standards to the set. All right, so today's systems, as they become more connected, as they have more features, they also have more risk for errors, for attacks, for just unpredictable events happening within them. And the challenge, of course, is to how do you build robust systems in these sorts of environments. And DDS really helps with this. We automatically handle things like network disruptions and anomalies, devices or endpoints can drop out and come back on the network. DDS automatically handles the reconnection and rediscovery of this. DDS handles dynamic network topologies. You can have multipathing. IP addresses can change. It handles unreliable network links, whether they're Wi-Fi, whether they're low bandwidth or high latency. And a variety of different sort of devices. Now, one of the really nice features of DDS is we'll talk about this rich quality of service. And again, what we're talking about here with quality of service is the communication behaviors of each of your data streams. And in your typical system, you're going to have a lot of different kinds of data streams. You're going to have maybe sensor data or streaming data. You're going to have command and control, maybe some real-time data there. You might have large amounts of data that have to go through analytics sorts of algorithms and processing. And each of those data streams are going to have different characteristics as far as what their timing requirements are, or what their reliability requirements are, or security requirements. And one of the nice things about DDS is to have this rich set of configurations that apply to each individual data stream in your system. All right, so let's talk just a little bit about DDS security. This is one of the more interesting aspects of DDS, and it's this ability to identify and authenticate each one of the endpoints that are in your system. You can provide access controls or permissions. So what is each endpoint allowed to publish and what is it allowed to subscribe to? And then there's also built-in integrity, validation, and confidentiality. So you can encrypt different data streams in your system. This is all built into the DDS protocols. We're not running over something like OpenSSL or TLS, right? Rather, we're, okay, I've got weird messages coming up on my side. It looks okay there. So it's integrated into the DDS protocols. So we still have this topic by topic sort of configuration. We still have multicast available. We still have this dynamic discovery. A lot of features that we're used to in DDS. There we go. All right, and DDS is scalable. I talked about this a little bit. You can use these same protocols, these same APIs across all kinds of different types of components in your system. You can also scale your system to lots of different devices. There's really no limitation on the number of endpoints that you can have within a network as you're communicating. So lots of different ways that DDS can be scaled. And DDS is widely deployed. We have decades of deploying systems with this software, and there are many millions of deployments spanning across all kinds of different industries, from aerospace and defense applications, ground applications, air applications, surface and subsurface applications, systems in space. NASA uses DDS very widely. To commercial domains. We saw some examples that Lynne put up for medical, energy, for transportation on and off road. DDS is found in a lot of different sort of systems and a lot of different sort of network challenge environments. Okay, so just to wrap up, the connected systems that we see today, that we're part of developing or that we see developed, have a lot of challenges in their network communication. And a lot of these challenges are common no matter what industry you're in. It's that question of how am I going to build a robust system given the kinds of constraints and the kinds of challenges I have in my environment, whether that's unpredictable networks or whether I have a very dynamic sort of network. Maybe I have to connect very embedded components with a lot of mobile devices or different RTOSes. Lots of different challenges, and DDS really helps you with all of those challenges. It makes it easy to take care of network communications, letting you focus on the functional requirements of your system and not worry about the details of how the data is going to get from point A to point B. All right. Yeah, any questions? Go ahead. All right, so the question was from a DDS Foundation perspective, has there been any work on looking at performance latency, and in particular, the difference between using a base DDS and a secure DDS? Now, from a foundation point of view, I don't think that's been part of what you guys have been working on. It is something that individual vendors certainly work on, and there are benchmarking information. I know if you go to our website, and I'm sure other vendor websites have information there too. I think at this point, I'm going to hand it over to Adam Mitz, who is going to talk in more detail about the DDS family of standards.
Hi, everybody. I'm Adam Mitz. I wanted to continue our discussion here about the DDS family of standards in particular. And I just have a few slides to show the standards, because when we talk about standards, there's going to be a lot of terms. There's going to be a lot of, three-letter acronym, four-letter, all those things. So there are links to the OMG website here. They're very simple, short links. So hopefully those are easy to navigate if you'd like to learn more about the specifications themselves. And I do think we'll have some time for some questions if you have to clarify what I'm saying, or we want to discuss a little bit more. But as Nina mentioned just a moment ago, we will have general Q&A time at the end of the session as well. So we're going to walk through some of the terms that you'll see around standards, and maybe this is like the less interesting part of this whole presentation, but hopefully I'll make it good. So when we're looking at these standards, you might think well, why is this a standard? Couldn't it be just someone comes up with, hey, here's my DDS product. It does all these great things, like things Nina was just talking about. Go ahead and use it, right? So the various technology providers came to the OMG as the standards development organization, said, for this really to succeed, it should be a standard, right? There should be a common definition of, well, what is a DDS? And how can different products that at least purport to be DDSs work together in a distributed system? So we'll see that as we go through these various terms. So first, of course, is just DDS. It's data distribution service. If you search for it with OMG, you'll probably find it. If you search for it without that, you'll find a lot of dentists. Another term that tends to come up with this is DCPS, that we might throw around that term a lot, data-centric publish and subscribe. So the approach that DDS takes to distributed systems is kind of summarized as data-centric publish subscribe. And the way I've described this or explained it to folks before, and others in the room may know more about this than me and may correct me on it, is data-centric, think about an in-memory cache, typed data that you can put in a well-performing data structure to use in memory, and that's great, right? That's a really useful thing. Lots of different products do that. And then there's publish subscribe, right? And that's a pattern that's been around for quite a long time. And the idea of, you've got kind of topic-based coordination. You're going to publish some things. Other nodes in the distributed system are going to subscribe to them. What if both of these two happened at once, right? So it's whatever that phrase or analogy was, the peanut butter and chocolate or something, right? We're bringing these two great things together, both the data-centric side and the publish-subscribe side, and we get a system that we found over the about 2 decades, we think now, has been really useful in many different distributed system problems. So what does this spec talk about? API and semantics, right? API means you've got different parts of a software system. You've got what we think of as the application, and we've got what we think of as the middleware, right? The middleware is the DDS stuff. And how should the application interact with the middleware? Typically within one process space, right? Sometimes people are saying, well, where's the server that I have to set up and deploy all these things for my queues? Nope, there isn't. Now you could have one if you want, but the standards do not mandate one of those things happen, and we'll talk more about that in just a moment. So you can set up these software systems with kind of well-known API, and not just the syntax of the function calls, but the semantics behind them, quality of service policies. And what do we get out of that? We get what I had on the third bullet point there. You get a distributed system based on asynchronous, strongly typed point to multi-point cache synchronization. And that's really what DDS is doing. So that's kind of a rephrasing of, I guess, of data-centric publish and subscribe. And it turns out that that's a really great kind of low-level distributed system pattern. And you can build all kinds of higher-level components and functionality on that. And people have, and it works well. So the next spec we'll talk about is RTPS. The formal full name sometimes is DDSi-RTPS. And we think of this as the wire protocol. And people may not be familiar with the term wire protocol. It's one of those terms of art in software. So when the software people look at, what's going to actually happen on the network, we call that the wire protocol, right? We need to get some bytes to send to the network stack, and how those bytes are formatted is the protocol. The DDSi-RTPS spec itself talks about UDP/IP, so we can use that in unicast or multicast. It's configurable in integrated reliability. So when it needs to be reliable, it can be. It does not have to resend every single byte that was dropped, but using the quality of service policies, it can know which ones are the important bytes that need to be resent if they happen to be dropped. Discovery is included in there. I was saying before, the whole question about, where's the server? There is no server. DDSi-RTPS specifies a peer-to-peer discovery, but it's also flexible, and you can do other things with discovery. People can and have and do put discovery servers behind it and all kinds of other schemes, and that's possible as well. Okay, that was the first part. Now I figure out how to advance the slide. Got it. Okay, next set of specs that you'll often see discussed, DDS security. So we spoke a little bit about security in a few different contexts already today. The DDS security spec, and as you're starting to see that there are these different specs that make up this family of standards, see how they also interact. So certainly you can have DDS systems that don't include DDS security, and they can be kind of in a completely closed, lab environment where you don't really need to worry about it, or they could run, within an otherwise secured thing like a virtual private network, and that's fine, and that'll work. But the DDS security spec itself has kind of DDS integrated ways of handling authorization, access control, and encryption, and provides these built-in implementations of these things, which would make your system interoperable with anything else that provides the same built-in implementations of these things, or you can customize it. And then there's the spec with the longer name. I tried to fit it all in one slide, so I elided some with ellipses here. Extensible and dynamic topic types for DDS. That's a very long name. We just call it X types. So the fourth of the major specs that I'm talking about here today is X types. So can you have a DDS system without X types? Sure, you can, and we did for a decade, 15 years, whatever, right? But X types brings a lot of very useful functionality to these systems, letting systems evolve independently, evolve their schema independently, and still work together. So it addresses the schema definition, the semantics of publish from one schema, subscribe to a slightly different one, how that's exchanged to the network, programming language mappings, including dynamic mapping, and the data encoding system, which has come to be called XCDR. Okay, in the interest of time, I will move forward. What else is in the DDS family of standards? There's a lot, so feel free to browse the catalog. The URL is there, a slightly longer omg.org URL, but if you're looking for it later, you can ask those of us who work on these things and we can find it for you. DDS consolidated, either XML or JSON syntax, the extremely resource constrained environments, in other words, like how do we run DDS-like systems on microcontrollers, the RPC over DDS spec, web-enabled DDS, the OPC gateway, Java and C++ platform-specific mappings, DDS for lightweight CCM. So just to let you know that they're there, right? Don't have time to go into detail on all these things. If there are questions on them, we could certainly cover them in the general Q&A that's coming later. And so these are the specs that you can find in the OMG catalog that are kind of explicitly DDS specs. There might be one or two others that I missed. If I missed the spec you worked on, I apologize. And then my last slide, what else is important to DDS systems and to the work that's going on here this week, for example, at the OMG technical meeting. Some platform type specs that are very essential to DDS include IDL and its language mappings. So IDL is the textual format that looks a lot like a programming language, like Java or C++ or C, but it's used to define the schema for topic types in DDS as well. And then, of course, we map that into different languages. Also coming from the platform side of OMG is the IEF reference architecture, which I do not have time to get into. On the domain side of the OMG, it's just good to note, and I'm also not an expert in these, but there are experts on them, even in this room, I believe, that these specifications that come from the domain side of OMG use at least some concepts. They don't necessarily always mandate this runs on DDS, but at least have some connection to it, using some of those same data modeling, system design, all those other parts of DDS. And that is just about my time, I believe, on kind of the tour through the family of standards. I will welcome Lynne back up to the podium for our next part.
So we'll co-share this while he gets the presentation. It's my huge privilege to introduce today's users who are going to be talking about their use of DDS. And let me give you a little bit of bio background on them. Christine Judd is the Vice President of Metron Inc.'s Unmanned Systems Division, providing resilient mission autonomy solutions for the defense, civilian, and commercial markets. With over 25 years of experience, Christine has advanced projects across the Department of Defense value chain, securing contracts with DARPA, NAVSEA, and ONR. Her experience spans analytics, autonomous systems, and applied simulation focused on autonomous solutions to solve real-world challenges, mission challenges. She currently leads Metron's autonomy software and vehicle development programs, focusing on platform development and intelligent, adaptive AUV mission planning, execution, payload management, and self-adaptive health management. Christine is going to come to the podium, and also welcoming to the podium is Matthew Judd, and he is the Autonomy Software Architect and developer of Metron Inc.'s Unmanned Systems Division, providing the same things, the same mission.
Same project.
Same project. He also has 25 years of experience and has also supported similar projects along with Christine. In the last 10 years, he has designed and implemented Metron's autonomy, navigation, command and control autonomy suite, which is the vehicle autonomy used for both commercial and Department of Defense applications. So my huge pleasure. Thank you for joining us today. Please join me in.
All right. So I'm going to give you a quick introduction as to what Metron is, what we do, to give you some context about what Matt will then say, how we use DDS and what are some of the challenges and uses that we have DDS for and how we used it. So let's see. Close that. Okay. All right. So Metron, our headquarters is located right here in the Ruskin Town Center. So it was a short walk for us to come over here. We're a small employee-owned company. We've got about just under 200 people now. Been around for a long time, since 1982. About 75 million in revenue, just to give you an idea of our size. And we're mostly PhDs in mathematics and statistics and physics and chemistry, as well as computer science and developers. Most of us with master's degrees. So it's that kind of company. We work for all of these logoed agencies that you see at the bottom of the slide here. So again, primarily defense. Across the whole board. So Navy is our primary customer, but we have several others, including the Air Force and the Marines. And for my division in particular, DARPA, the Defense Advanced Research Projects Agency, is our primary client. So R&D development, I'd say applied R&D development. And again, particularly our division works for a DARPA office that is very interested in having technology demonstrated at the end of their program. So they have a 2 or 3 year program. They want to see these vehicles in the water, on the ground, doing what they're supposed to be doing and performing the missions that they've laid out. So Metron as a whole, we do data analytics, looking at large amounts of data and figuring out what are the anomalies in that data. We do autonomy, which is what we're talking about, decision support systems, modeling and simulation to varying degrees, all the way from large campaign level simulations all the way down to, again, what we do, which is more individual units, hydrodynamic modeling for underwater vehicles, that kind of thing. And also the sensing side. So we often say, an autonomous system can't do anything if it can't sense the environment, right? What do I make decisions on if I don't know where I am? Okay. So what are we focused on? So we have this kind of theme tagline called resilient mission autonomy. And what does that mean? Again, we're like, autonomy is great. It's interesting, how do you do it? But at the end of the day, autonomy, just for autonomy's sake, isn't worth that much. So why do we do autonomy? Because of the missions that the mostly defense, but also some of the commercial areas ask us to do. And those missions are generally long duration. So we're not talking about a few hours here. We're talking about days, weeks, months, even years. So these systems have to be resilient, right? They have to understand the environment that they're in, and then have to understand the decisions that they can make in that environment. So that's kind of the mission autonomy side. And then they also have to understand themselves, right? What is my current health? How can I mitigate the fact if my rudder isn't turning quite as well as I thought it was? Those kinds of things. So external autonomy and introspective autonomy is what we call those two things. All right, so since I can't talk a lot about the stuff that we do for defense, we also have commercial endeavors that we're getting into. And what are we really talking about here? For our underwater vehicles, we're mostly talking about offshore energy. So when these offshore energy companies decide to put a wind farm somewhere, they have to do a whole sequence of things that are mandated by the government, starting with site surveys, and then while they're constructing it, they have to do construction surveys. Once everything is built, they have to do, infrastructure maintenance surveys. We're talking about, following a pipeline, making sure there's no cracks, making sure that there's no subsidence under it, or it's covered when it's supposed to be covered. So these kinds of things. And right now, they do these inspections from a surface vessel of some sort, and ROVs, remote controlled vehicles. So that takes a lot of people, it takes a large boat, it takes a lot of time. What they're starting to explore, and what we're involved is having these large underwater vehicles go out there and do this all autonomously. So some of the things, I kind of mentioned a few of these, but visually inspecting it, using different sensors at different times, so switching systems on and off, understanding whether I'm on track or off track. All of these things kind of go into that, as you can imagine, if you're out there for days and weeks and months, in order to bring back this data at the end of the day to the customer. So this is kind of an overview of what we do. I'm now going to turn it over to Matt, who's going to talk particularly on where DDS comes into all of this.
Okay. So now it's going to the specifics of how we do it. So a lot of the things we've just been hearing about are the things I was focusing on here. So our first use case is we actually develop the system. So what does that mean? So We have to simulate the world. So there's going to be a pretty high-powered computer in the network that's running the simulation, and that has to feed the data to our system that we would be getting from real sensors. Then we've got our actual deployed autonomy. Our target, the vehicles we run on tend to be power constrained, so we are usually running on low-powered computers, ARMs, like, iPhone kind of computer system. So it's really, I don't know it's as low as some of the standards I've seen. They were for very resource constrained. I don't think we're using anything like that, but we are, it's not a really big high power computer. And then we've got some tools for monitoring. I'm going to talk about this more with the post-mission analysis, but our GUI that we use for live monitoring when we're running in sim is Java. A lot of the people developing on that are Windows. So we're already talking 3 architectures, 2 languages. So having something like DDS to support that is really important. Trying to implement that, at the byte level is nightmarish for anybody as old as me who has done it before. So we don't want to do that ever again. And so what I'm listing there on the right is, so those are the 3 architectures. And I heard somebody, previously talking about the different kind of data flows. So the sensor data tends to be same size. There's not really a lot of variance, high frequency, and the guaranteed delivery is not that important. You don't want to get backed up. So if you miss one, you're just going to get the next time. Command and control messages are intermittent. They can be vary in size widely, and it's really important you not miss any of those. So those right there are 2 different use cases. And then we have a set of messages I call the monitoring messages, but there's a whole lot of data that we publish that is really for us to figure out what happened once we get the vehicle back and pull a bunch of data. So those are really important for our PMA, and they're very important in this development phase when we're live monitoring. Once it's out in the water, they are lower priority than the other things. So it's a good range of the topic requirements. All right, so which one is it? All right, so the deployment, like I say, so these are power constraints. So once we actually put it on a vehicle, these are large vehicles, but from a computer system standpoint, it's a small number of computers. So it's a closed network. We're not, a lot of the kind of capabilities we were talking about before, recognizing new machines popping up and going away, or dealing with network problems. These are not our problems. We have got one connection between 2 physical bottles. If the line is broken, there is no way adapting to it. And so one thing I do call out, so something that capability that we're getting from DDS, or from our vendor at least, that is really important is a logging service. So just log every DDS message published for later use. So that's really important. Our base system is a small number of processes, usually on the same computer. But one of the capabilities we're trying to support is, different use cases. We'll have a payload or an extension, possibly in a different bottle, where we just define the interface of the data we want to get back and forth, and we don't have to know how they're implementing it or why. So DDS is obviously very good for that. And again, so on the right there, I'm talking about the requirements on this side. So now there's no Java, there's only the AMD. I meant ARM there, but it's only the low powered message there. And like I say, the PMA messages at that point are really low priority. All right, then the analysis. So the way this tends to run is the vehicle is out there for some length of time. Like Christine was saying, some of these missions can be really long. We're going to be logging all the data that we can. Sometimes that data gets really large. And the first thing we do when we pull the vehicle out is pull, gigabytes of data off of it and try to figure out what happened. And so this is where a lot of the capabilities from DDS and using this structured data has been really important. And so we're going to show a little video after this of a tool, the tool we use for post-mission analysis. But all the data that we show in that video is logged DDS messages. And in the past, when we were developing a new machine, a new vehicle, as well as the autonomy, we could use that data to go and identify a wide range of failures, including actuators breaking, getting caught in a fishing line, and the vehicle changing direction in a way that we didn't think was possible, a lot of other things. And the important thing that we got out of that was we didn't know before the mission started what data was going to be important to figuring out the failure point. So being able to capture all of the data that flows across these pieces and being able to access it quickly and visualize it really speeds up the development in an analysis problem. Yep.
Are you able to adjust the velocity?
So we're using RTI's native logging system. There's a lot of configuration in that. I haven't had to explore it yet. We haven't used this for a multi-week mission yet. I'm sure it can. I'm sure it can. So that will get really tricky once we start trying to do that. Like I say, we don't know which data is going to be important. So we don't want to tune it down too much. I'd rather throw more disk space if possible. But yeah, so that even our long missions, like I say, these vehicles are power constrained. So if it's a really long mission like that, it's probably spending a lot of time with everything off. So there's not a lot of messages flowing. All right, so what else did I want to say on this? I think that's mostly what I wanted to say. So I didn't have any pattern to follow of what you're looking for in a use case. We could get into details if somebody cares about the specifics of the message, but the point is it's exactly what previous speakers are saying DDS is useful for. We can identify the structured data in IDLs. We share it across teammates. Several of these processes on these vehicles are implemented by other performers on these contracts. So as long as we agree on the structured data, it doesn't really matter how they're implemented, and that has worked really well. Any other? Let me see. What was the last slide on here? Oh, that's the video, which isn't there. So we could. So I could start the video and talk to it. No, it's not. But what it might be publishing, and so the system we were working on with that, it might be publishing the actual length. So that was a linear actuator. So some of the data it was publishing was like the actual length of the actuator, and we know for a given length what that should interpret as the angle of the rudder. And when all of a sudden, it went to a certain length and the rudder stopped moving with it, we could interpret that as
Or temperature starts running away. I actually worked with that LDUV program in Prototype a few years ago, and the way you handle that is DDS has a deadline quality service where a publisher can say, I'm going to send you a message every 5 minutes or something like that. If it fails to make that, they'll both be notified. So that's probably fine.
well, so we're probably talking about two different things. What I'm saying about how we use the data to analyze, it was actually publishing data that was not in the command and control critical path, but I just had it publishing state so that in this PMA phase, I could load that data and see it, right? So I'll have to talk to you later, because with the LDUV INP is when we started doing all this.
Yeah.
So we actually were working on the ONR's initial program that turned into LD. So,
And I guess one thing I didn't say that is actually very important here is when these vehicles leave the pier, they're gone, right? They're no communication, no anything until they, hopefully come back, right? So, so that's why this logging is really, really important.
Lynne is marketing. How much time and money you saved by using DDS rather than?
so that's an interesting question, because I have been doing this kind of thing for a really long time. I started using Corba 1.0 when I was in college, so 30 years ago. So before we used DDS, we were using active MQ and string or proto kind of stuff. What I would say DDS is really giving us is we are starting to work on systems that might potentially transition for the Navy. And the fact that DDS is an accepted technology on programs of record is not true for the kind of free things we were using before. So pub sub systems and structured data save so much time. It's like most of what kind of things we do, we couldn't even bid if we were actually going to go and try to write byte, things that were to and from in byte. But the DDS, I mean, the implementation works. So we swapped between vendors at one point pretty smoothly. So from a DDS standard viewpoint, that's probably good. So all right. So this was just a video that we made to show off our GUI to our customer. So the point is not really the GUI, but the point is all those the timelines over there on the right, the red data is basically vehicle state data, so things like depth, speed, heading coming at a pretty high rate. The little blue dots in those same timelines are the values we're commanding. So one of the things we can see from this right away is the vehicle actually following what we command. So that's the kind of thing we'd want to be able to pull out of it. Yeah, so there's a whole bunch of stuff in here about. So there is a whole lot of data, timeline-based data, more than we'd want to look in any particular view. So some of the things we're calling out here is, if it turns out what we really care about is roll, then we might want to add a timeline about roll. But all that data is captured in the DDS messages. Yeah, so here we're looking at commands. We're drawing a little map. So there's in that data is a lat long depth, so we can overlay it on the map and see the path.
Ignore the fact that it looks like it's on land. It's just that the bathymetry data is great. This is Narragansett Bay in Rhode Island.
So
Very shallow. So
we used to test off of San Diego, and we keep being promised we're eventually going to demo in Hawaii, but those always turn into New York or Rhode Island by the time we get to that date. I know. I believed it the first couple of times. So so here on the right, you can see as we're changing target headings in blue, you can see the vehicle kind of catching up. I think that's heading. We're tracking the RPM versus speed sometimes. You can see the depth. The point of this is mostly we are generating a whole lot of data during a mission. We don't know what we care about until and literally all we know when the vehicle comes back is it came back, which is, a successful day. But we don't know if it just, go spun around randomly and came back up or actually did what we wanted until we start looking at this. Like I said, our target vehicles are really long duration, and my nightmare forever has been it happily loiters and needed death until the batteries run out a week later. So I'm always happy when it comes back. Anyway, so the point of this was really just to call out we are capable of using only the data that we capture off the DDS to do the vast majority of our analysis. And when something fails, usually, and we're still working on getting some of our autonomy specific structured data in here, which also flows over DDS. So sometimes we have to go down into logs to figure out why the vehicle made the wrong decision. We're trying to get more of that information into this. But anyway, so that was the point of it. I think that is all we had planned.
We have a set of questions here, and we decided to give about 5 to 10 minutes for each one. So the first question I'm going to ask is, Andy, could you describe an application of DDS that's interesting or novel, please?
Yeah, so great to be here. Thank you. Most recently in the news that's interesting and exciting, at least to me, was NASA's use of DDS in Kennedy Space Center. The Artemis launch, which was history-making in many ways, but I was really thrilled to have some of my RTI teammates be involved in that project. All the data in the control center, everybody has an image of the control center with the old-style tubes and the multi-floor control center. All the go or no-go flight decision data is flying around over DDS to decide whether this mission can take off or not. Mission critical, yes. Real time, low latency, lots and lots and lots of data points in that space, and they're doing just fantastic stuff that I used to read sci-fi in high school, and now they're doing this stuff, and it's running over DDS. So I think that's pretty interesting.
So you guys have anything else to add? Eric?
I'd like to go back to sort of the cradle of DDS. That's the Naval Combat System, because it very well demonstrates why DDS evolved in the way it is. If you look at a naval combat system, there's a lot of sensors that gather a lot of data. Then there's actuators, which normal people call shooters. They need a lot of data to actually hit the target. And then there's a lot of processing that needs to be done to correlate all the data and feed the actuators with the right data. But of course, a naval ship is a target itself, and it needs to be resilient. If it gets hit and it doesn't sink, it needs to operate with what it has left. And so what you typically see is that some of the processing units are so vital, you don't want to lose them. You don't want to have a single point of failure. And so often what you see in traditional systems, if you double them, you know, the master and the slave, but you can only transition once. If your master is dead and you transition to your slave and then your slave dies, sorry, you're out of business. What is so nice about DDS is that DDS doesn't need the concept of master and slaves. You have sensors, you have actuators. As long as they're connected and as long as there's processing power somewhere in the connected network, you can have your processing applications run. Data gets automatically routed to them. And if they die for whatever reason, you just respawn them somewhere else in the system. The traffic will reroute to them. And what is specifically DDS is very nice. Like if you have this track table consisting of all the information that you need, DDS just gives you, if you respawn, like, hey, here's the latest track table for you. You don't need to do anything. You can just start immediately. So that's really cool about the technology.
Thank you. Yes.
Yes, let's see, I'm going to go into the medical field. So one of the clients that we work with has a couple of different departments doing different medical stuff. So we've got devices that work in the OR, actual like cutting instruments and sensing instruments within the OR. And then there's monitoring tools that would be used in, for example, patient rooms in the hospital, or even at home monitoring tools where remotely doctors or nurses or care providers can get information about how a patient is doing at home. And then as part of their suite of products within hospitals, they also have this ability to pull usage data going back into their server farms to do analytics on usage, trying to do predictive maintenance, those kinds of things. So if you look at these systems from a data communication perspective, we've got in the operating room, we've got a wide range of devices. Some are very capable 64-bit ARM sort of processors. Some are very low powered. We're talking ARMs that might have 256 kilobytes of RAM, just very, very small microcontrollers. To like kind of standard maybe Windows systems that are controlling the patient monitoring tools, and then the nurses stations that have to monitor all of them. Those are kind of interesting because they get deployed into a hospital network. So the device manufacturer doesn't have control over is multicast going to be available, for example. They don't know from one hospital to another what they're going to have in that sort of environment. And then, of course, it's the large amount of data that gets collected. What they do is they have a technician come in with a tablet that will come in, turn on, connect to the DDS network, and find all of the devices that are within that hospital, which ones are available for maintenance, and they'll do software updates, and they'll grab usage logs to take back and do processing with. So it's a really interesting mix of sort of data requirements. We've got DDS security going on within all of those sort of hospital streams. A lot of patient privacy sort of issues that drive them to DDS security. They have, of course, robustness and reliability requirements. The testing that they do on these systems, they will run 300 copies of their devices for 14 days straight and see what kind of failures they get. This is the sort of strenuous testing that has to go through before things get deployed, and DDS, of course, works very well. Someone had asked, I think, earlier about the savings. You know, what do you notice when you use DDS? Did it save you any time or any money? And this is one example where they had a couple of different cases of this. They had their installation period. When they go install into a hospital, they used to have, I think it was like a 2 or 3 week installation period. Each device had to be configured, given an IP address, configured for where it was going to be sitting and how it was connecting to other devices. And they've cut that down. They now do like 3-day installations to a hospital because of DDS and the dynamic discovery process. There's just so little configuration that happens. And then another interesting point I thought for that cases in the development cycle. So they had a development cycle where they do the development of their software, and they have somewhere near the end of that, they have allocated time to develop their test suite for all of their like simulation devices and their test harnesses, and then it goes into integration. And they got to the point where they're developing with DDS and doing just their normal use case tests that they do through development. They got to the point where they were supposed to be developing test harnesses, and they were all done already. And they didn't even realize the time saving that they had when they were doing their development until they got to this point, and they're like, well, we have a couple of months allocated and we don't need it, we're already done. So yeah, medical.
So to add, Adam.
Yes, so the application I'd like to throw into discussion here is IoT, Internet of Things, and closely related IIoT if we want to distinguish industrial Internet of Things. But there's lots of different kinds of distributed systems that could be considered IoT, IIoT. But one application space that might be familiar to a lot of us is something simple like a home automation kind of device, right? So you could buy a device, let's call it like a smart door lock that you can install at home and have connectivity from your mobile phone, and you can lock and unlock. It's great. That exists. There are many of those kinds of systems around. Is DDS an IoT technology? Well, not just an IoT technology, but DDS can certainly be used to build IoT systems like the one I just described. And so why would you do that, right? Why use it? What we found is that since DDS is flexible and adaptable to where it's deployed and to different kind of network models, it is really well suited to this kind of application. So very similarly to what Nina was just talking about different kinds of embedded up to like full-size computers and everything else that's going to be deployed to. This Internet of Things application has a similar aspect, right? So your embedded device, has a small microprocessor on it. Your mobile app, runs on Android or iOS. And there's probably in this kind of system some kind of cloud component involved too. And so DDS domain participants can also run in the cloud, and these can all talk with each other in all kinds of different combinations. The one that we found really compelling here as well is peer-to-peer. And what do we mean by peer-to-peer in this context? Well, a lot of the communications that would go between, the mobile app and the home automation device don't need to bounce up and down the cloud, right? They don't need it. Like once you've established security documents, you're allowed to control this lock, everything else that happens behind the scenes to make a secure DDS system work. The peer-to-peer connectivity model says, we can have those cloud servers kind of as a backstop, right? If our network routes just don't let us go direct, that happens, right? These networks are unpredictable. You don't know what ports are going to be blocked, what multicast is going to be blocked, and all those kinds of things. So the cloud part of it is important, but it's also important to see use of it strategically, right? We want to directly control the devices when possible and have that cloud system as a backstop. Another aspect of this that we found really interesting and compelling is the scalability, right? So if you're looking at your own personal deployment in a home, you may have a few locks, you may have a few people authorized to use those locks. That's a pretty small scale thing. What's really happening behind the scenes here is that, well, we're not going to deploy a separate cloud server for each homeowner, right? So the backend systems in the cloud that run these are scalable and can talk to tens of thousands of devices at a time and do that securely and efficiently. We found that has just been a really interesting use case for DDS, and it touches on many of those different aspects that we talked about for this afternoon, including DDS security, because we're not going to put messages out on the public internet without DDS security, or security of some kind. X types, right, to allow flexible deployment with schema differences, and many other things, which I think it's probably time. So.
Yes, it is. Thank you. So this question is for Eric. What are the advantages of DDS to other network middleware systems and solutions?
I think most people, when they compare DDS to other middlewares, they're comparing it to message queues. And they say, I have my message queue, it does everything I need. Why would I switch to DDS? And I think that's the wrong question. I think that the question should be, do you really need a message queue? What you often see is that people build all sorts of stuff on top of the message queue to do what they need to do. And so two of the things I would want to highlight about DDS is DDS has the concept of keys. And a key allows you to identify a piece of data as like uniquely identifiable, like rows in a relational database. And that is really nice if you want to decouple systems in time. Because if I send you a continuous stream of updates and you don't have the time to consume each update, you just can every now and then check. It's nice that DDS sort of places these updates in the right rows in the database. And when you have time, you just take a look at your database and say, okay, this is the latest state of all my rows. And so I don't need to do that in my application. If I would have a typical message queue, I would be consuming all these messages, putting them in a database, and that comes for free with DDS. The other thing that is really nice is the durability service, where basically DDS keeps copies of these database tables for you, for if you're late and data was already published ahead of you, you can just get the copy. You don't know who you're getting it from, but that's not important. You just start as if you have always been there. Or if you get disconnected and stuff is published while you're disconnected and you reconnect, boom, your database table gets updated automatically and you're back where you need to be. That's the sort of stuff that DDS can offer that typical message queues can't.
Andy, do you have anything to add?
Yeah, so the competition with an existing queue or an existing system, more broadly, it's competition against thing I invented already, the thing that I already built and have blood, sweat, and tears put into. Why would I look at DDS as an improvement solution? And the answer I like to give is because you get to leverage the 20 years of experience that's built into that spec. With DDS, you're picking features from kind of a menu. I want to add ownership to manage my reliability. I pick that feature, I enable the quality of service, and it just works. It solves that problem. It has already solved that problem in 15 other use cases. For these particular framework communication issues, these are solved problems. Why would you want to do it yourself and maintain it yourself and do it wrong the first time you do it yourself versus just choose a working implementation? So I think it's a value add that it's hard to measure because it's just a paradigm shift. You're picking from work solutions and deploying them so you can focus on what your application does that makes your application different. It probably isn't the communication, right? It's just a necessary evil to empower these wonderful applications.
Adam, yeah.
Sure, yes. I think building on what Andy was saying, that's excellent. And the way I was seeing it is just to kind of step back and say, it's a fairly high level view, right, of data sharing and distributed systems, as opposed to these like lower level approaches, like I need to, build a message out of these particular bytes and figure out what address to send it to. And so I think that's one of those advantages that we have to keep in mind, right? That there are other approaches to doing these sorts of publish subscribe style data sharing, but DDS really does keep it at a pretty high level, which lets the application developer concentrate on, as I was saying, things that matter to the application developer. And another aspect of it that I wanted to highlight on this was the, because it is a fairly high level system, there are some costs to that, right? We should be honest about that. But given all those things, it's still very performant, right? And it meets needs in lots of different spaces. Nina.
Yeah.
Yeah, I think it's important with DDS to look at the whole suite of features that you're going to get, that you just don't get all of these from any particular middleware, whatever it is that you're looking at. You got to look at the dynamic discovery part of it, along with the rich quality of service, the 20-ish sort of policies that are available to configure your individual data streams, along with the interoperability that you have. You're not vendor locked. You can get an open source version. You can pay for a commercially supported version of it. If you need something that's going to work in this particular environment with my particular language that I'm using, you can find a DDS product that does it, and it will interoperate with the other component of your system that doesn't have that. You have the wide, well, speaking of programming languages, you have the wide programming language support. I don't know what other middlewares out there are out of the box supporting C, C++, C#, Java, Python, Go, Rust, just a whole bunch of different programming languages. And again, they're all interoperable. They all work no matter where you're using them. So there's just this whole list. I probably missed some security. There's this whole list of things that you get with DDS. And you might get one of those or two of those with another middleware product, but I don't know of anywhere you're going to get the whole suite of things.
Before we,
Yeah,
yeah, good.
DDS, and I'm a little fixated on the security part. But if I'm using DDS and I'm not using the security plugins, and then I decide that I want to use the plugin, how difficult is it to use the plugins after the fact?
It is both easy and difficult. Do you mind if I field this? On the one hand, it's very easy because you don't have to change any of your existing code. It is simply when you initialize DDS, there's a little bit more configuration that you add to that one call. And that's it. So you don't have to change any of your existing design of your topics, any of your existing codes setting up those DDS entities. But it is challenging because you have to know what your security architecture is, and that's not easy. You can't just go, oh, I'm going to turn on security, done. Right? You have to know, all right, these are all my endpoints. What permissions are they going to have? What happens if I get an unauthenticated participant in the network? What do I do then? All of this stuff is configurable. Which topics have encryption on them, which are in the clear? Am I going to protect the metadata or just the application data? So all of these things have to come together in your security sort of architecture, and that part is usually not easy. It takes some time.
But totally, you have to, as you said, that it's just in the configuration. You can't just turn a plugin on. You've got to turn it on, but you've got to configure it to your
Right.
needs.
And the good news is that's outside the DDS API, right? So you can develop your whole system without security and then go back and apply security.
But security is systemic, right? We're talking about DDS security, which covers the transport, the movement of that data securely. But you've got multiple other security concerns in and around your system to have a fully secure system. DDS can help with a portion of it, and one of the trickier portions is managing the certificates that all of the secure communication is based on. If the certificate is compromised because you didn't have physical protection to the machine or network, sure, right? It's part of an overall system. So that's why it's complicated. And you can dumb down DDS security to be one stop. Just fully encrypt everything, throw it over like a security blanket over everything, like some other technologies make you do. But you pay extra for CPU and you pay extra for bandwidth if you choose to do it that way. The granularity, which brings the complexity, is what lets you pick and choose and have a very specific profile for your application.
Even if you do that, still.
There's one other thing to consider is that with DDS security, you can have a heterogeneous environment. So you can have some nodes that are running at a high level of security and some nodes that are running at no security. And they can interplay when it's allowed and not when they're not allowed. So for example, you can have an unsecure publisher sending data into a secured subscriber or vice versa, and you don't have to worry about it. It is built in.
Thank you.
Thanks.
Let me move on. Actually, that was a question I was going to ask them later, but we've already answered it. So that's what I'm going to skip. So the next question I'd like to ask the panel here, and I'll direct this one to Nina, is what's new in the DDS family of standards?
Okay. So something very new happened this week. We actually formally adopted a new standard into the DDS family, which is the DDS TSN standard. So that is very hot off the presses new. I think one of the interesting things about this DDS family of standards is that it is continuously evolving. So when we talk about what's new, it's not just a new standard that comes out, it's the fact that the original DDS standard that was done almost 20 years ago was first released, is still getting updated and re-released. So even the standard that's 20 years old is still new or still recent as we're maintaining it. The same is true for the RTPS, that wire protocol that's gone through multiple revisions as we add additional functionality and additional features to it. DDS security, of course, is one of the important ones because security is always changing. The threats are changing, the encryption algorithms that we use are changing, the other technologies related to handshaking are changing, and it's important that the DDS security keeps up to date with those technologies. I'll just kind of give you an overview, and these guys can talk about their favorite new standards, but some of the ones that have been recently released include the consolidated XML, the ability to, in XML, basically define a DDS application. You can put in all of your DDS entities, all of your topics and data types, all of your service, put it all into an XML file, and then your code base is very small. You just kind of put it in and start reading and writing. And then some of the standards that are in work include the API standards for Python and C#, I think, are in work right now. And I think there's a TCP over DDS that's in work right now, just to kind of give you an idea of what's available.
So let's see, Eric.
I'd like to say something about TSN. Maybe not everyone is familiar with what TSN is. TSN stands for time-sensitive networking. And so originally DDS was employed in typical Ethernet systems with classic IP networks. And IP works great, but IP is not a deterministic protocol. Messages can be lost during transmission. And so they might need to be retransmitted, and the retransmit may be lost. So you never know how long something takes. And that is probably fine. It's non-significant if you're operating in, let's say, the millisecond domain. But if you want to go down to the microsecond domain, it's just not deterministic enough. And so the concept behind TSN is that you get specialized hardware that has synchronized clocks in the microsecond domain. And this hardware actually has built into it the ability to define a global schedule. And in the global schedule, everyone is involved. The switches, every network card, and according to the global schedule, everyone knows when it's time to be allowed to put something on the network. And as long as the schedule, let's say, fits the system, you can make sure that if you send a message, it gets across and it won't be lost during transmission. Why is that great? That's great if you need latencies in the term of microseconds and you need that determinism. The thing with the TSN spec as such is you need to have that global schedule. And that, for the traditional, let's say, TSN engineers, is a lot of work. They need to handwrite a schedule. They need to make sure that everything fits. And what is very compelling to TSN engineers is that DDS is quite the opposite. Like, it's spontaneous. There's spontaneous discovery. You exchange all your demands and requests. And so what is opened up with this spec is that you can map the DDS principles onto TSN principles. And so you could basically allow a system to discover, like, who is there, what are their desires, what do they want, compile a schedule out of that, and then check if the schedule is realistic, and then facilitate it. And yeah, that's a win-win situation. DDS and TSN map really nicely.
Adam? I wanted to highlight a little more detail two of the works in progress specifications that Nina briefly mentioned. One is TCP. So as I mentioned, when we did the overview of the family of standards, the wire protocol that's standardized for DDS, which we call DDSi RTPS, just RTPS for short, because that's a lot of letters, works over UDP IP, is flexible within there, right? You can do IPv4, IPv6, unicast, multicast, all that stuff. But some systems or some deployments would really rather work on top of TCP. And many DDS implementations already support some form of TCP. I don't want to say all because I don't know the details of every single DDS implementation. The one I work on certainly does support TCP, but there's no standardized way yet to do DDS, RTPS kinds of messages over TCP networking. Yeah, standardized. And why do we want to standardize it? Well, not just because it helps it be correct and robust and good, but so we can interoperate so that different products can exchange messages that way. So that's TCP. If you're listening to this and you're a DDS user and you're interested in that, I think the foundation to say would definitely be interested in hearing your feedback on if that's an important spec for you to prioritize. And the other one is C#. So and really maybe .NET kind of type system and family of languages, what we call it C#. As those languages, net system has kind of evolved from its beginnings as a very Microsoft-centric technology to now being cross-platform, to being much more open. We're seeing more adoption of C# as a programming environment for DDS applications. So getting a standardized API for that, I think, okay as well.
Andy?
Yeah, I just want to go back to TSN for a little bit because I think that has a potential to be a game changer. Even before there are full tool support that do that planning, there are a lot of applications that need that reserved bandwidth, that ultra low latency delivery of the messages that's going to be available with TSN. The hardware, the level 2 hardware that supports the TSN as a transport is governed by a different set of specs, right? Hardware IEEE specs. Right now, if you buy the hardware from the same vendor, it works pretty well. I think that's going to converge as well. It's going to get cheaper, and we're going to be able to do things in a way that we can't do right now with DDS because it doesn't have this ultra low latency support in the hardware yet. This is what's coming on board. The nice thing as a system architect is you can now use DDS as a data model across your whole system. Not have to do little hardware things on the side, but have an overall system model and then build systems of systems, layered systems that lets your whole application and whole enterprise deployment or worldwide deployment of your system happen all over DDS. That's going to be greatly enabled by this new spec. It's not really new, right? It's been built, it's been in the process for years, but now it's a new official specs people can start to depend on. I think that's going to be a game changer.
So let's turn our attention towards interoperability. Yeah. Do you have any questions? I see a hand right there. Anybody on the chat? Okay. Yes, sir.
So I don't think really a question. I'm cheating, but none of that's what I would call the newest thing in DDS. The standard, I think the newest thing is the adoption in some of these other industries. Automotive has gone from not being able to spell DDS to assuming it in almost every new design for the software-defined vehicles and zonal architectures. And UMA, we're just going to talk about another big adoption in underwater vehicles, and there's a lot of activity in that. I think is TSN is cool.
Maybe Stan's question is, where has DDS been recently adopted and standardized?
I don't know.
Thanks, Sam.
No, it's an excellent point. Excellent.
Right.
It is, yeah.
I had a question. Forget, we were just answering.
Any other questions?
Oh, I'm
Yes.
sorry.
I had a question. I want to go back to DDS security. And I've worked with security, but it's been a dozen years ago. I've noticed recently the Intel family of processors has an AES 256 cipher built into the chip. So you can offload all that encoding, decoding. Does the DDS security support the hardware acceleration that's available in the Intel chips?
Yeah, so DDS security,
Yeah, whoever, go ahead.
Go ahead, whatever.
DDS security as a specification is kind of silent on that, right? It's up to the implementations that use the DDS security spec to build, systems, right? To build DDS libraries, essentially, that to determine exactly how they'll use software and hardware features of the platform. So I think, in a sense, it's not on that, but also the selection of kind of the default ciphers that are in the DDS security spec are exactly, AES-256 GCM, AES-256 GMAC. It's all very industry standard ciphers, and that's why you see it being picked up in both, off-the-shelf software solutions that you can, freely download. The CryptoSO has it, but those solutions can also, make use of hardware acceleration, and then DDS would make use of that.
Yeah, and the only reason I asked this, 12 years ago, I wrote an AES 256 cipher in the DSP, and oh my God, it was just a crawl,
Right. So if we took that DSP on, a board that, has CPU on it that's going to run the DDS libraries, you could certainly, have those things work together, right?
Run in parallel, yeah. Thank you.
Yes, see, the problem with the DDS security, if we move to autonomous unmanned vehicles or ships, so the data itself could be compromised by the sensors, by firmwares, modified during maintenance, and then the autonomous systems basically go into accidents, life can be jeopardized. All this security that you're talking about, it just handles the encryption and the authentication, but doesn't handle, is this data that my autonomous system is getting is trustworthy? It has not been compromised. So that's what we need for the DDS to be deployed into unmanned autonomous system, whether vehicles, whether aircraft, and it is really missing. We are working with the Navy on this issue, but I see it like, security is not authentication and authorization. I could do denial of service attack and kill off the communications, whether it's encrypted or not.
Well, and like Andy said, right, DDS security is a part of their whole security solution.
Yeah.
It is an important part. You do need identification and authentication of your endpoints. That is going to help make sure that the data that you get, you know that it's coming from where it should be coming from. And so DDS handles a lot of that, but it doesn't handle everything.
But that's not security, only the confidentiality, integrity, right? It doesn't handle.
Well, it also handles identification and authentication of your endpoints. And it handles the key negotiations that happen in there. So you do have assuredness that the data that you're getting comes from who you expect it to be. That is part of this.
And additionally, it can be part of a zero trust solution because you have a profile that says if I'm a publisher of this topic, by definition in my secured profile, I'm not allowed to listen to topic B or publish on topic C. I can only do what I've been provisioned for. So you can build a whole zero trust solution across all your nodes.
I am compromised.
Yeah.
I meet all this and I still destroy the system, right? If I am an insider, well, this is a fact, right? We cannot ignore it.
So DDS security is securing the DDS domain, right? And it's the tools that we think will be really useful parts of an overall security solution at a distributed application level. But it can't do everything. It can securing the DDS domain.
But if I move to an autonomous system, I better address these issues.
Sure.
Can I comment?
Not at the comms layer, I don't think.
Not in the comp layer.
Take back to the DDS PC.
May I comment on that? So DDS, when the data is in motion, that's what the DDS security handles, the entirety of the data in motion. And the problem you're considering is, what if that autonomous submarine gets compromised, gets captured? So what you really got to focus on is how do you secure the data at rest? The data at rest is your certificates and things like that. And if there's in DDS and the durabilities, as long as you're not using persistent, the data is stored on a physical hard drive. It doesn't need to be a DDS security handler, but if you're using persistent data, which is stored on a hard drive, then you need to make sure the data at rest is secured.
Take a self-driving car, and you have a traffic light and it has been changed to 45 miles. What do? You have a pedestrians crossing, and I remove that pedestrians from the self-driving car. What happened? That person will die. It is not the encryption. It is not the authentication. It is the data itself that being fed to the autonomous system that has to be zero trust. That means authenticated, authorized, and there is no severe consequences if I take the actions. That's
Well, there's a couple additional things that DDS here does provide, which is security logging, so intrusion detection. There's a standardized way to do that logging, typically on a separately secured channel, so you can be made aware of that. Classifications that are standardized as a way to try and help manage the overall life cycle of the data. But as I said in the beginning, DDS can only be responsible for the data.
It's great technology. We are using it. I'm not saying it, but we are in fact in our Navy project. We are using it. What we are building is to address the data piece that being fed in the DDS. Make sure this data that the autonomous system is making decision based on is trustworthy. That's where whatever plug-in that you have is really not addressing it.
All right, I'm still happy to work with you to address it. Yeah.
I would love to. Okay.
We'll discuss more.
Yeah, so let's move on. The next, we had, one of the questions we were gonna address was the whole issue of DDS security. I think we've already thoroughly covered it. So, I'm gonna move on to, talking about interoperability. And, let's see, Adam, what are you doing as a vendor to support it, interoperability?
Sure, interoperability is it's a pretty large topic in the DDS world. There's a lot that goes on to make different DDS implementations interoperate with each other. We've had sessions where we've gotten together at this meeting in Reston and plugged a bunch of laptops together and just gone through, okay, here's what needs to happen to get all these systems to work. But more than that, and more than the demos that hopefully people have seen, if not, we can provide resources to them, are the real kind of on the ground experiences. So, I have experience with, one of our clients was, using our solution, OpenDDS, in a mixed system that also had another DDS in it, and said, hey, certain things just don't quite work, right? There's one corner case. It is basically interoperable, but we found this one corner case, right? So it's those experiences of, really, the kind of on the ground debugging, got to run Wireshark. It's useful, and you can get those problems solved. But we're doing a lot within the foundation and within the DDS PSIG to have, test application. There's a test application available publicly on GitHub that assists with interoperability testing as well. And I'll try to keep this short because I would talk about interoperability all the time if.
But it has priority. If we find an incompatibility, yesterday, no, this morning, yesterday we had a DDS meeting where we actually talked about one of those and yeah, we.
I think
we
anything
give it
with
priority.
face-to-face, it usually comes up one thing.
Yes.
I think there's two main apps. I mean, if you're asking kind of what we're doing as a vendor to support interoperability, I think there's two main aspects of that. And one is just on our own, and not alone because we can't test interoperability on our own, right? But we do kind of on our own work with these other vendors of DDS products to test as we release a new version, as they release a new version. We're testing interoperability as the standard updates and there's a change or features in the standards and we update our versions, we do that testing. That testing is not exhaustive. There's a lot to DDS. There's a lot of different configurations of DDS, and then you go through all of the different vendors and their whole suite of deployed versions of their software and how they intermix with everybody else's deployed versions of software. There's a lot of stuff. Like Adam said, there's edge cases. Maybe I'm using a data type or a configuration of a data type that was not in our interoperability testing, right? And it just hadn't been tested. And so there are issues in the field. I'd like to say that for the most part, interoperability does work, but you do find issues in the field. So that's the second thing that we do as a DDS vendor, is that's a extremely high priority for us. If any of our users are in that scenario where something isn't working the way they expected it to, some of my data is not getting through, or I'm not matching, or none of my data is getting through, or whatever the case may be, that's a high priority for us as far as technical support. And we will go and we'll look at network captures and try and debug as best we can what's going on. And sometimes that results in coming back to the OMG, coming back to the PSIG to try and clarify or update a standard. Sometimes that results in code changes where we have to actually put together a new build to account for this scenario that maybe we didn't account for before. And sometimes it's working with another vendor to say, what we thought we were doing it right, but you're doing it different. Like what is the case? And we do all of those things as a company to support interoperability.
Andy?
Yeah, I think we pretty much covered everything. I mean, the interesting part is you have to have, even if we come across an implementation that needs a rework and a fix, you still have to support the other customers that expected it to work with the old interpretation. So all the vendors have to manage the priorities of all their customer bases. There is an intersection where things are interoperable, but I know from my perspective, we're on 80 targets across 3 generational releases of the product over 20 years. We've still got some of that code that's running in the field, so we're sensitive to forwards, backwards, and cross interoperability. It's a challenging problem.
Thanks.
That's why we do it.
I think we have time for one more set of questions, after which I'll kind of open up for more questions from you. Yeah, I've been looking at the clock. That's why I'm doing this. Keeping count of time. So unless you don't want to answer this last session. Okay, great. So the last one would be the question about the need for common interfaces on top of DDS for certain application domains. And Adam, you're the one that wanted to be the lead on that.
I'll try to answer this quickly. Yeah, so there's a common concept in system design called an ICD, right? An interface control document, and definition, whatever it is. But we see the same kind of pattern happen in DDS-based systems. So it's not enough to say we're going to use DDS and we're all going to work together, especially in distributed teams that will develop different parts of the applications and hope for them to work together. We really have to have a common understanding of, data types, topic names, domain IDs, quality of service policies, security policy, all those other things. And we've seen sometimes organizations can do that kind of internally with different groups or departments kind of working together. We've also seen that happen through standardization, whether formally like an OMG standard or more informally someone just publishing, here's how we do it. And there's a number of examples of that.
Okay, Nina or Andy, do you have anything to add?
Well, you do have to pay attention to things as simple as units. Just because you use DDS doesn't mean that my value for temperature magically works at the receiving side unless you pre-orchestrate it to agree that the units match, the scale matches. So building some layers, I think they're more conventions than standards typically, but you have to have a way to expose those conventions across the teams that want to have the application level interoperable. That's crucial.
Can I say something about that? Because that's essential. An Ariana rocket that exploded because the units didn't match, right?
Kilometer versus mile per hour.
Yes. So with IDL4, you can actually put annotations in your data model that specify what your unit is. And those annotations are taken into account when data types are matched because they determine the hash of the data type. So we could detect those clashes and we could notify you that there's a mismatch. So it is something that you can benefit from it, but you have to put the effort into specifying what your units, and same thing for ranges. There's annotations for ranges, for units. It's all in the language, but you'll have to specify it.
Okay, I'm gonna close this up because it's drinking time,
Yeah,
right?
yeah, well, we got there. Trying to.
So I think DDS type safety is a whole nother conversation that if you're interested in, we should have because it's a huge benefit of DDS. But kind of going back to the original question of, you know, is there a use or do you build common interfaces on top of DDS? It's natural, right? I mean, we don't program sending IP messages over the network anymore. Why? Because we'd rather use UDP or TCP. Well, we don't even do that much anymore. We used to open up sockets and do that, but we don't do that anymore. Why? Because we can use DDS. Or maybe you're using something like MQTT or I don't know, but you should be using DDS. And it's just natural that that keeps building, right? You get all of this new feature and functionality out of a technology. Well, you make use of that and you build something better. And that's what happens. And it happens across all industries. And I think Stan was trying to give us a bunch of examples with that, with AutoSAR, with the automotive industry. DoD does it all over the place. FACE for airplanes. GVA for ground vehicles, TMS for the tactical microgrids that go in forward deployments, and then you see it in commercial, and you see it with jet engine test harnesses, you see it in connected ORs, automotive, of course. So it happens everywhere, and it is a very natural thing to do.
We have, I think we'll have time for one more question because I can hear the crowd out there. Comment.
Quick comment. Interoperability. I've actually done interoperability with RTI. Zeta Scales, Open Splice, DDS. Andre Odermatt and I did a face interoperability where we not only communicated interoperability with the DDS level, but with the face TSS level, same face interoperability. And I've also done interoperability with OpenDDS. And in both cases, Andre and I gave him my source code. We had it interoperating in about an hour. And my customer that wanted me to prove interoperability with OpenDDS, I did that in half an hour.
Very good. Thank you.
Well, this is another comment on that interoperability, and probably is a different viewpoint on that. So our exposure to that has been through the spec, which got mentioned. So it's an ONR, fairly complicated spec to support unmanned vehicles. That spec has gone through some really wide changes, in part to come up with a common subset that multiple vendors can support. As an end user, it has made the spec not worth following until it stabilizes. So that has been a real problem from a user viewpoint, that the spec has to keep changing to try to be able to be supported by multiple vendors.
Thanks, Dick.
Try not to do that with
I was
DDS.
looking around and trying to figure it out. I said, oh yeah, it's there.
I was talking.
Oh,
That's okay.
what? Oh, you were.
Yeah, I was.
It just sounded like it was.
I'm
sorry.
right. The speaker's right.
It's only Wednesday, and I swear to God, by the time Friday comes, I'm gonna drop dead. So anyway, so I will seal this place to you.
Thank you for coming tonight, dealing with our little technical challenges, and we appreciate it. Thank you. Thank you to our panelists and our speakers, and anyone online that has additional questions, we'll email you back.
Well,